Hi everyone, this is the last video that I'm going to do was related to meiosis. In the notes it's referred to as chromosome mutations. So chromosome mutations are where, or the example that we're going to look at is non-disjunction. So with a chromosome mutation, the chromosomes are incorrectly separated either during the first meiotic division or the second meiotic division. Now the example that I'm going to go through involves this non-disjunction during the first meiotic division. I'll reiterate this at the end. It can happen during the second meiotic division, and you can probably work out how that would happen once we've been through this. Okay, so here we see a diploid cell at metaphase, so in that second stage of meiosis, metaphase 1, the first meiotic division. Prophase 1 happened previously. That's when the homologous pairs of chromosomes paired up to form their bivalents. Perhaps crossing over happened previously. At metaphase 1, this is where independent segregation would take place. So we can see how I've randomly placed the paternal and maternal members of the chromosomes on one side of this dotted line which represents the equator. At the poles of the cells, here we have, these are the centrioles, and at this stage the centrioles have spread and moved towards the poles. Spindle fibres have been left behind, and those spindle fibres attach to the centromeres of the chromosomes. Here we can see the chromosomes existing as the sister chromatids, pair of sister chromatids joined by a centromere. Those sister chromatids are the product of DNA replication. Okay, now we know with independent segregation they could line up randomly on either side of that equator. Now, normally, at this stage, metaphase 1 progresses into anaphase 1. And let's show these chromosomes at the top. Slightly differently. Struggling here. This chromosome will be pulled towards the towards their poles, like this. As the spindle fibres shorten, that pulls on the centromeres, and the chromosomes get pulled towards the centrioles, towards the poles of the cell. And we can see here, normally, like we said in the previous videos, that during meiosis 1, the homologous chromosomes are separated. Okay, that's a normal division. However, sometimes, and this is rare, but it does sometimes happen, a process called non-disjunction takes place. And that happens when both members of the homologous pair move to the same pole during, well, we're going to say anaphase 1 for now. I'll come back to that in a minute. So, if that were to happen, if non-disjunction took place, let's say that both of these homologous pairs, both the paternal and the maternal chromosomes are both pulled towards this pole. So we can see that this homologous pair has been unsuccessfully separated. Top one, normal, successfully separated. This bottom one, unsuccessfully separated. both members of that homologous pair have gone in the same direction. Now, what will that mean for the daughter cells that are produced after that first meiotic division? Well, what's this? What stage is that? Okay, what we would find then is, so all three of those cells, all three of those chromosomes, so one homologous pair and one individual from a homologous pair, would all end up in this daughter cell here. So let's show that with, now I'm going to show this as metaphase 2. Okay, so prophase 2 has happened in here somewhere. Let's progress on to metaphase 2. I'm just going to change that slightly, give myself a bit more space. That would mean at the equator in metaphase 2, we would have, I'm going to draw them slightly differently this time. Actually, two of those longer ones, out of space there. Both the maternal and the paternal of the longer homologous pair, and we're going to end up with a paternal of the shorter chromosomes. Okay, so we've got 3 chromosomes lined up. There's that homologous pair that were unsuccessfully separated, and there is the single member of the homologous pair that was successfully separated. That's in one of the cells. In the other cell, that's this one here, well, we've just got that member from the successfully separated homologous pair, so that's one of those shorter chromosomes, like so. And they form, or they line up across the equator, across the middle of the cell in metaphase 2. Now metaphase 2 progresses into anaphase 2. And in this situation, well, we know the second meiotic division, so I'll write it in here, meiosis 2 separates the sister chromatids. So the sister chromatids, well, they're on either side of the equator in both of these cells. So this top cell would end up with one of the longer maternal chromosomes, one of the longer paternal chromosomes, let's colour that in to show that they're different, and one of the shorter paternal chromosomes. Let's make them a bit longer so we can differentiate. See the difference. Okay. So, it's still got this unsuccessfully separated homologous pair here. Really, there should only be either a maternal or a paternal, as we know from our previous meiosis explanations. This one's going to be the same, so it's going to have a longer maternal, a longer paternal, and then the shorter paternal. Down here, okay, we've only got that member from the shorter chromosome. This is one of those maternal chromosomes. They become separated, so we end up with that and that in both of them. Okay, the problem with this is that we've now gained an extra chromosome in these gametes. Okay. So, what we should have found from this diploid cell, if it had successfully separated, the haploid number which is, if we remember, n, should equal 2. So n is the haploid number, and that should, if it successfully separates, equal 2. What we found then in these gametes, so that haploid number should be 2 in the gametes, well here we've got n plus 1, n plus 1, and these are n minus 1, n minus 1. Now, what tends to happen is those cells that are n minus 1, because they don't have the genes present on these chromosomes, those chromosomes that they are missing, these tend to be non-viable, so they tend to die. However, the gametes which are n plus 1, so they've got a haploid number plus an additional chromosome, can persist. If one of these gametes, n plus 1, fuses with a gamete in fertilisation which is n, we're going to end up with a cell with an additional chromosome. And those cells with additional chromosomes are referred to as triploid, i.e. they have an additional copy of one of the chromosomes. So we've got some examples of that. You may be familiar with the first one, which is called trisomy 21. Now the other name for trisomy 21 is Down syndrome. Trisomy describes that there are 3 copies of chromosome number 21. Okay, so there was unsuccessful separation of the chromosomes, meaning that a gamete was produced with 3 copies of trisomy 21, its haploid number was n plus 1. It fused with a gamete where there had been successful separation, so it ends up with 3 copies of chromosome number 21. Okay, that's Down syndrome. There are others, and if you've got family members that have recently been pregnant, they may have been offered screening for these. They are trisomy 13, which is another name is Patau syndrome, and the last one that's available for screening is, or another example, is trisomy 18, which is Edwards syndrome. All 3 are as a result of this non-disjunction, unsuccessful separation of the homologous pairs, meaning that gametes are produced which are n plus 1. Those n plus 1 gametes combine with a gamete with the normal haploid number during fertilisation. When they do that, one of the chromosomes has an additional copy. Okay, trisomy 21 is the most common of these. Down syndrome producing trisomy 21 is more common than Patau syndrome, and I think of the 3, Edwards syndrome is the least common. And in fact, with Patau syndrome and Edwards syndrome, it's quite common for that fetus to not reach partum, not reach birth. Okay, let me just check that I've got everything in there that I want to say. I suppose one thing you could say, this is the case in humans and animals. In plants, it's much more common. Triploid. Triploid cells are quite often produced, and they increase the genetic diversity of that species. So, for example, if you've got one good example of that is bananas that we eat. They are triploid, meaning that they are unable to produce gametes, and that's not always the case if something is triploid, but in bananas it is. Unable to produce gametes, so they're unable to produce seeds, so our bananas do not contain seeds, as another example. That's non-disjunction. It's a final little bit on meiosis. I hope that was helpful. Remember, you always feel free to email me, leave a comment in the space below if you've got any questions. Right, take care, look after yourselves.